Okey. InsyaAllah kita mulakan dengan membuka Al-Fatihah. Okay, first of all, apologies that I cannot turn on my camera because of the certain condition, because I still am at home. Okay, so we're going to continue what we left. So hopefully it's not too long in such a way that we need to recall a lot of things. So maybe there's a few things that we're going to recall in order to understand what we're going to cover today. So if I'm not mistaken, that we left with the Ampere's law, and that is somehow can be related with the Fleming left-hand rules. So hopefully you still know that. You should able to revise, recall, try to recall yourself using through the notes, and also you can go through the exercise. Then if you do have any problem, you can always ask me. You can telegram me personally, or you can ask your respective lecturer that in charge in your tutorial. Okay, so the method of we're going to cover tonight, I'm going to go straight away deliver the lecture. Okay, I will not stop asking whether you understand or not. Straightforward. But if you do have any question, then you can stop me anytime. Even if I maybe explaining too fast, and you can also stop me anytime and then ask me to re-explain that particular thing, or you want me to explain in a different language also can. And even if I were, you let me know lah, which part that you want me to explain. Okay. So I already explained this one regarding the MPS law, how that circle integral, closed integral, will lead you to a value, closed integral of a magnetic field. So this one is given you is a magnetic field. You multiply this particular magnetic field strength and with the particular length, and then sum the whole operation there will give you until you reach back to this particular point. The sum of that will provide you the permeability of free space with the enclosed current. By means of enclosed current, in this case, enclosed current here, for this example, will equivalent I enclosed will be equivalent I1 plus I2. And then if you remember that this the value of current is also uh, is also corresponded to the direction of current. Okay, the direction of current means that in this particular case, since that both of them are upwards, so if I were to have the current I1 as 1 and then the I2 is 2 amperes, so then the total will be 3. But if there were a case that the I2 here instead of upwards is going downward and then the magnitude is still 2, so let's say this is I1 is 1 ampere and then I2 is 2 ampere. So the I enclosed here will be 1 plus minus 2. So that will give you a negative 1. Okay, if that was the case. Okay, so
Yeah.
okay, sorry. Okay, coming back here. So what does it mean? It means that the net current, the total enclosed current will be negative 1. Okay, means that all these two current we can just replace it to equivalent. So of course it will not be like this. So we can replace the two current into just a single uh, one single current, which is going to be I enclosed equal to -1, which is downward lah. Actually, the -1 means downward. With respect to this example. And then the direction also, you can always check whether there's consistent. Then the enclosed current, the direction of the enclosed current should be consistent with the right hand grip. Right hand grip. So this is your thumb of right hand, and then your finger. Okay, so something like that. So my drawing is not that good, and I cannot share my camera. So something like this. I hope you get my picture here. Okay, so this is your right hand grip. So this is your hand. Okay, so the thumb here indicating the direction of the current, and then the right hand grip is the direction of the. Oh, this one I got it wrong again. Should be the opposite direction. Okay, the thumb is the direction of the current, and then the other fingers, the other four fingers, showing the direction of magnetic field. So in this case, if you look at here, the thumb is upwards, and then the other fingers of your right hand would give your fingers like this. Like that. Ni ada kuku sikit. Okay, so then this is your thumb. Very weird hand there, but I hope you get to understand. Okay, so like that. So then if you look at here, this is the direction. Oh, that's not the right color. Okay, so this is the right direction. Okay, same goes with the example here, and then the thumbs point upwards, indicating the current. So that's for the example. But if you look at my other example here, you will have your right hand grip there would be on the opposite direction. Would be, of course, if you put it this way, you're going to have your thumb here, and then so this is the back of your finger, and then you will see that your okay, so your thumb there. So you're going to be opposite. So this is the downside of your hand lah. And this is too much. I think should be somewhere only here. Panjang sangat finger tu. Macam tu. Okay. So what you're seeing here, the thumbs point downward, and then the other fingers will go point this direction. So it's consistent to the direction of this current, at the magnetic field. Or you can also use this thumb the other way around, in a way that the thumb point to the current, to the magnetic field, and then if you look at here, the thumb is pointing at the magnetic field, and then if you try to make it in such a way you can see the thumb there. Okay, let's say if I were to put, because this is the direction there, okay, following to the other side of the direction, and then if you put the thumb there, and this is your thumb, and then this is your other fingers, you're going to be curved in this direction. Okay, so what you're seeing here is the thumb here. You just imagine it's trying to hold this this loop. Try to hold the loop. You try to imagine this. The red line here is technically is a physical loop. So you grip on that loop. You grip on that loop, and then that red loop will be in your grip. In your grip, yeah, you will see that the thumb, the other fingers will be from the back of the loop there, and then hooks. Sorry, hooks. And from the back of the hook, go in front of the hooks. So you will seeing that it is from the back goes inside here. From the back goes inside here. So that's showing that the current is going inside the loops, following to the direction of the thumb here. Okay, so something like that. Try to try to imagine, or you can play around. So this is the same example I show you just now. But as I mentioned just now, you can also use the other way around. But means that the representation of the current can be for the thumb can be represent the magnetic field instead, and then the other fingers pointing towards the direction of the current, whether it's going into the loop or going out the loop from the bottom or from the top. It depends on the and your uh, perspective lah. Okay. So this is the equation for a single uh, wire, single wire, infinite long. So that's why usually we call it a long wire. We cannot use it for the short wire because they're going to be different. If we're going to, we can't use it. We can't have it as an approximate like this, lah. So usually going to be, we always have a statement there for long wire, lah. Okay, so where the magnetic field is, the magnetic field is at this point. So that point, the magnetic field will be at this point, and then the value of current is this current. Permeability is the constant. 2 pi is 2 pi. What about R? R is from this center towards this, okay, to that distance. So that will be the distance R. So if I were to ask you what is the magnetic field at this point, then this one going to be is R, the radius. Okay, so it's always at, it's not the radius of the wire, but the position from the center of the wire towards the position that you would try to determine what the magnetic field. Okay, if I were to have another radius outside much more further, then this one will be the radius, from the center as well. Okay, so that will be the value lah. Okay, so we're going to go a little bit more further on the example later, where you're going to apply that radius in many places, many ways. Okay, for circular coil, so the what you're seeing here is technically kind of like inverted of the situation that we are dealing with a long straight wire. So you're seeing a curve structure. So instead, the curve, the circular uh, circular figure there is represented by the magnetic field in this case. But here is the wire itself, means the current. So if you look at here, it's technically kind of like inverted. Okay? Instead of having the magnetic field circling, okay, in circular geometry, we have the current moving at circular geometry in this way. And then you can again you can still use this right hand grip, pointing your thumb, as I mentioned just now. Only that this in this case, the wire is in the circular geometry. So then you will have your thumb here. Okay, your thumb in that direction, and then your finger. Try to imagine that you're holding the what you call it, the loops here, the hoops. Sorry, the hoops, and then see the finger here is at the back of the loop, and then your point finger will be in front of the loop, like that. Okay, so this is another finger. So same goes, and then another finger, and then another finger lah. So this is your palm. Okay. Okay. So the back of your hand, you're holding in the hoops. So if you look at here, from the back goes in front. So from the back goes in front. So this is the consistent to the direction described in this figure. Okay. So hope you able to get that. Okay. So the thumb is pointing to the direction of current. Same goes what we have done here. Okay. At the back, and then point the finger there. Okay. So in this case, you can also use the same thing as I mentioned just now. You have the what you can do. You can invert. What you're seeing here is the thumb pointing towards the direction of the current. Okay, but but you can also do it invertly. That one going to be very useful when we're dealing with this kind of for solenoid. Because what you having the hoops there, the many hoops is not the magnetic field, but the current. Okay, so because there's many hoops, and then the magnetic field. So what you can do, you can have your thumbs here, the right hand thumb. Okay, let me try to draw it, although it's quite difficult here. Okay, this is your thumb. Okay, your thumb will be pointing at the north. Okay, pointing at the north, and then same goes here. Okay, I think we can just make it the outside here, so then it's easier. So we try to make your hand, your palm hand, uh, holding this whole loops. So again, you're going to be at the back, okay, at the back of the hoops, and then you're holding this, and then your finger will be on top of the loop, from the bottom, and then goes, and then on top of the loop here, okay, something like that. Okay, so if you look at here, so this one is a little bit tricky because you need to be careful. Okay, so this is the point up, down, up here. So when you're pointing upward in the hoops, in the loop here, in the solenoid, make sure that the direction arrow here is the outside part. Because here, if you look at, yeah, I think this diagram, what either I read it wrong, because it's very confusing here. Okay, so yes, I think I read it wrong here. Yeah, because you can't actually see it. So this is actually on top, This is actually on top. Okay, so then this is the top one. This is going to be the top one. This one going to be the top one as well. Okay, whereas the current out here is this one at the back. This one, the one in front. So it then goes to the back. Because we can't see actually which one in front and okay. If you look closely, then you'll see that this diagram. You can see that the black line here. Okay. Something, I think, yeah, the one is at the back, Okay, I think this diagram is somewhat wrong, the direction of current, is somewhat wrong. It shouldn't be this way, okay? If you look at that, the current, following to this, even if you use the same way, the current and the pointing of the direction of current. So this one is not current in, this one is actually out, This one is in. Because if you look at this one is the one at the top. Okay, the one at the top, so means that the current here should be on this direction. Okay, so following to what I see just now. Okay, right hand grip. Okay, yes, I double check it. Yep, it's still right. Still should be that way. So this one at the top, as I mentioned just now. Okay, so there's a error there in the loop there. Okay, so if you look at this is one at the top, the one I label is all of them are at the top. So this one is the current is input here. So the thumb is pointing to the direction of is pointing at the north pole, at the north pole, and as well at the back of your at the bottom of your hand. Been mean by the bottom of your hand this side lah. This one. What I mean by the bottom of your hand is this one, the one I highlighted. This one. Oh, I think I accidentally moved it too far. Let me just scroll it back quickly. Okay. Okay. So like that. Okay. So remember, you can also use this one using your right hand grip. Only that the use of your finger is going to be inverted instead of having your thumb pointed to the direction of the current. You can use it to the direction of the magnetic field, and then you should remember the magnetic field outward from the north. Is outward from the north going to the south. Okay, means that your thumb is always point towards the direction of the magnetic field. It's not pointed to. But if you, in this case, you're going to have the thumb at the same position as the north pole. But it's technically it's pointing towards the direction of the magnetic field. Okay. Okay, so this is just permeability of free space. This one also you can get it through your calculator. Okay, so this is what I already mentioned just now. Okay, the strength of the if it can be increased due to kind. So this kind of facts, in terms of the strength, you can always visit or look, refer to to this equation for all of these three conditions. You can see how the magnetic field varies with its configuration here. So the magnetic field will increase if you increase the current, but it will also increase when the radius is decreased. Means that the closer it's towards the center or near to the wire, the greater the magnetic field. Same goes with the logic or the experience that you have. Whenever something is closer to the magnet, the pulling the force of the magnetic force is going to be stronger. So means that the magnetic field is stronger as well. Same goes with the wire. So for the circular coil, in this case, we're going to be a little bit different here. You will see that the magnetic field here will also so the same will be greater as you uh, increase. Technically, the center of it is going to be the maximum. But the magnetic field, okay, I should first tell you first. I think I didn't mention you just now. Okay, the magnetic field given here. Where is the magnetic field given here? The value that you calculate using this equation will give you the magnetic field at this center, at the center of the wire coil. So the magnetic field given here is the 2r here is 2r is no, not 2r. The r here is the radius of the coil of wire here. And but the magnetic field given here is at the center of the coil, at the center of the coil. And of course, the current is also increased. So this one is based on the number of coil. Yeah, the more the if it given by this example, there's only one. So this n is going to be equal to 1. But you can have this a number of round of wire. Same goes as solenoid. Yeah, it's only that solenoid is very it's not just a short line of wire, but it's a very long of wire. It's a single layer of wire. Okay, so that is number of coil. Okay, so 2r is at the center of the magnetic field. Center of the magnetic field. So in this case, we for the circular coil, we try to negligible that there's a significant kalau kita wind tu from the side, kalau saya gulung wire tu, kalau saya ada wire, so wire tu kalau kita gulung-gulung ni, kalau saya tengok daripada tepi sini, with my eyes at this side, my eyes at that side, I will see like tire lah. But from this perspective, this length is negligible. Maksudnya dia tak tebal. Will not be because once you have a significant length for this, then it becomes solenoid. Okay, the magnetic field is no longer you can determine it in such a way that the magnetic field will be uniform. So compared to this, the magnetic field will not be uniform along the within the circle of wire here, where the center is being given. The center of the magnetic field will be given by this equation, but whereas for the solenoid, the magnetic field here is given by somewhere at the middle here. The condition is that the solenoid need to be long enough, and then the B here will be at somewhere at the center, between the length of the solenoid, somewhere at the center here, but it not necessary to be at the center of the within the circle, within the loops. Okay, so that's okay. And then this n is actually is a number of n over L. So the other form of equation of this, you can have it in terms of mu n I over L. Okay, so this n of this small n is actually number of coil per length. Number of coil per length. Okay, so this is what I mentioned just now, the proportionality. You can always play around with the proportionality for all of the equation. So if you look at here, if I have more n, then it's going to be macam ni, so 1, 2, 3. Okay, so if I were to add 4, then there's going to be more magnetic field inside here. And there will be more magnetic field. But if I were to have 1, 2, 3, 4, if I have the same 4, but I stretch it into longer length, so means I increase the length here, then they're going to be the magnetic field here going to be less. So the current is still directly proportional for all of the cases. You can increase the current, you will also increase the magnetic field. Okay, so this already explained just now. So that's the permeability. So this is also, I think you already know. Okay, you can also play around with the check with your right hand grip. Okay, so you can check your right hand grip. So I think all of you know the dot referring to the current out of the page. And then if you put your thumb in such a way pointed outward, so this is like your thumb pointed out from the page, and then you will have your finger like this. Your finger like that, and then so on there. So so ni tangan awak lah. So ni thumb ke atas So the thumb is outward from the page, and then your finger will be like this. So technically it's point out this direction. So this is where you get. Okay, so the current. So in this case we use the thumb as a current. Remember, it can be used the other way around as well. Okay, but for this case we use the thumb pointing to the direction of the current, and then the all other index finger and the remaining fingers will point to the direction of the magnetic field. So you can also play around with the opposite direction. So this is how it look. When we show you just now, technically we are trying to see from the top, so we're going to see something like this. So this is also considered a dot. It can be put it this way, or you can just put it a single dot that will referring to the current is out of the page. So that's how you write down. Or you can put it out of the screen, but it's easier for you to write down. It's much more common sense if you put it out of the page, because whenever you have to deal with this kind of answer, the diagram will be on the page of the question, the examination question. So it's either it's out of the page or into the page. Sometimes it's just X, sometimes it can be a circle with X. So that one is into the page. Remember the analogy behind these two, so that you don't get confused, is the analogy of an arrow. Okay, the point here, the front is going to be point, just a single point, but at the back, if you remember, we have like kind of like feathers to navigate the arrow, so we can simplify that diagram in terms of like X. So if the arrow leaving you, then you will see, the first thing you will see is the back of the arrow, which is X. But if you see the arrow is going towards you, then you will see the point of the front point of the arrow, which is just a simple dot. So that's how you can describe or to avoid confusion whenever you need to identify the direction of the current or magnetic field. We still use the same symbol. Either it's current or magnetic field, the same symbol. So this is the same thing. You can also test your use your note again, check your notes, and then try to you apply or use your right hand grip, whether it's consistent to the direction of current and follow by the direction of the magnetic field. And then also you can also use uh, the direction of the thumb as a magnetic field, and then you will eventually uh, could navigate the direction of your other fingers, the other four fingers, to the direction of the current itself. Okay, it can be used the other way around. Okay, so if we go to the example here, what is the strength of the magnetic field at a point of 0.5 from a 50-meter wires. So 50-meter wires, just to indicate that this is a very long wire, but you won't be using it. Okay, but if the question is say that uh, from a 5 centimeter wire, so then this question need to be questioned because you can't use this equation if it that short. because it won't be accurate. And usually this equation only valid if it long enough. Okay, the approximation will be more accurate, will be long enough. If not, it won't be that accurate. Okay, so coming back to here, the distance, what is the strength at a point of 0.5 from, so that distance, it means that this is a wire, that will be the distance. Okay, and then R is the magnetic field here. So as I mentioned before, this distance from the source of the current and the source of current to towards the point of your magnetic field that you're looking for. So that will be the value of radius. Okay, so that value of radius. The other thing is just follow to the what is being given by the equation. Permeability, you find the value. If you do forgot, learn how to find the value through your calculator. Despite of any different calculator, so ask around. Ask your lecturer. In the tutorial session, you can ask your lecturer how can you get your permeability constant through your calculator. Okay, and then the remaining is the same lah. Okay, so let's go to the next one. Okay, this also have the solution, so I think I can just explain the solution. Okay, a long horizontal wire. A long horizontal wire carries a I1, where it's 20 amp, so given in the figure there. A current in the positive x means that this is going to be a positive x, means that towards the right is positive. It's already indicated, so you need to follow to the direction indicating that the right is on the towards the right is positive. And figure below, a second wire is 5 centimeters. So the position that separate between the two wires is 5 centimeters. So calculate the magnitude and the direction of the magnetic field midway between the two wire if the current I2 flow in the same direction of I1. So given in the figure here is the same direction. So follow the figure for case A. Okay. So the question asks you midway. Midway means that midway. So this is y1, this is y2, separated by 5 meters. But the question asks to calculate the method and the direction of the magnetic field midway between the two wires. So the full way is from this wire to another wire. Midway is mean that half of the way, middle of the way. So middle of the way is going to be at the very middle between the two wire here. We're going to be the distance from here to there will be 2.5 centimeter. So remember, be aware of the unit. Once you got the idea how to solve this, be aware of the unit. Make sure every unit is converted to SI unit. And that is the rule of thumb, the easiest rule of thumb you should remember. So to avoid any mistake, if you can't figure out what is the question, what the least thing you can do, although you're not going to be given any answer, any mark for that, but make say you somehow able to figure out, you can avoid this loss of mark by simply convert every value that's been given to you into SI unit. You can just simply right away, for 5 cm, you can just update this 5 cm immediately, just simply like this, or you can just immediately put it like this, so you aware what is it and what is the value, and you can also change into the question whatever it is, because in this chapter you will no longer be evaluated or given a mark your method in converting the units, but you can always make use of the unit conversion that you have learned, which is much more safe, it's much more clearer. You can write it down slow and steady, take your time, and then try to avoid more mistake. Okay, so to avoid mistake, you can just apply the same method, although that method will not be given any marks even you got it right. Okay, so you need to remember that. So I ask you for your own safety, because we don't want to have you're going to lose a few marks because of the uh, because of your you forgot to provide a proper unit. So then you will provide you a wrong answer at the end of the calculation. Okay, Coming back to this, so that is the midway. Okay, so since that this is a long wire, a long wire, so then if you refer to the three on the equation being given to you, there's a three condition. One is for long wire, we have B equal to mu naught I over 2 pi r. So another equation is for a circular wire, where B equal to mu n I over 2r. And then another one is for solenoid, where mu small n over I, or this one also can be written as mu n over L, the length of the solenoid, multiplied by I. So only these three too. So if you look at this condition, which one is the appropriate or that is fit to this situation, it's going to be this equation. So first, you identify the equation, and then second is try to make use of what are the information given here. So remember again, after you know, remember again, read again the question. Okay, it asks you calculate the magnitude and the direction of the magnetic field midway between the two wires if the current I2 flow. It doesn't ask you okay, I2 flow in the same direction I1, but it doesn't ask you the magnetic field due to I1. Okay, if you look at this equation, this is just B, and then this is just I, and then this is just R. Okay, so what does the equation mean when you input the value I1 here? So then this one immediately become I1, this one become immediately B1, and then this also become immediately R1. Okay, let me just read there's a comment here. I didn't catch up with the comment just now. What was it? Oh, I think it's not in the comment. It's not quite sure. Oh yeah. Okay, noted. No, Nabila, you sharing the device. Hopefully the sound is clear. So hopefully you benefit from it. Okay. Okay, coming back to here. Okay, so make sure that you take that value I1. So it's not going to be B2 here. So what does it mean here? The magnetic field that you are measuring, which is from the R1 designated from the midway here. You are looking from to the midway here. Okay, so that will be that. Why is it moving here? From the, so this one is going to be 2.5 centimeter. That will be the R. After this one haven't been converted, make sure you convert it. And then the I here. So this what you're seeing here is the magnetic field due to current I. So means that this is what we are calculating here is the magnetic field that is provided, that is caused by the current I, not by current 2 yet. Okay, so that is okay. So the question asks you the magnetic field here, but it doesn't ask you the magnetic field there at this point due to I1 or due to I2. It's just asking you the magnetic field at point there, at that point. So if you look at here, so the current I1 will provide magnetic field at that particular point. At the same time, eh, current 2 also going to provide you another magnetic field as well at the same point, R2. So this going to be R2. Of course, going to be 2.5 as well in this case. Okay, so then you just simply put an I2 there, put the R2 as well, and then put all the values. Put the values. But okay, so technically right now, what from there we're going to have a magnetic field from current 1 and then magnetic field from current 2. Okay. Okay. So the next one, because it asks you the magnitude. So since that we have two magnetic field from a two different source, and then at the same point, of course, you're going to have what we call it a resultant magnetic field. So resultant magnetic field, as by described by the name itself, is just summation of all the magnetic field. So in this case, we only have two, B1 plus B2. But remember, okay, so this magnetic field have a direction, and the direction is corresponding to the direction of the current. How can you know the direction of the magnetic field at that particular point? Is by using your right hand grip. Okay, again, if you look at here, if you imagine, okay, so imagine that this is the thumb. The thumb, you try to, okay, so because the thumb in this case going to point to the direction of the current. Okay, going to point to the direction of current. So you remember, you try it like you holding this wire. Okay, so you're holding so your hand is at the back, your finger will be in front, and you will see that the direction here will be from there like this. Okay, so what you're seeing here, this is like curve, like curve. Okay, if I were to see from this side, exactly from this side, what you're seeing here is the current. This is for I2, and then the current, this is for I1. Okay, and then because of the what we discovered just now, it's going to be counterclockwise. Okay, look closely. So this going to be the position 2.5, and this is not, this is just a label. Okay, the label not pointing any direction, just a label there. 2.5 centimeter direction from the current is also 2.5. Okay, so what you're seeing here right now, that magnetic field going to be like this. Okay, but if I were to further this direction, it's going to be like that. So if you look like this, if you really draw a perfect circle that overlap that point that I given to you, you will see that at this particular point that I mark here, that point, that particular point will have the direction tangent, tangent which going to be point downward. Okay, you have to imagine that, because this is like a flat surface there. Okay, then when you have a circle pointing, let me just fix this one, pointing at the surface there, and so then we can make a circle there, and then at this particular point, that direction will be downward. Okay, so although this curve, and then this was slightly curved, but at that particular point, beside adjacent here, it's going to be downward. So how can you know this? Okay, any point here, if I were to show a point here, and then I point the line from the center of the wire there, so then this one also going to be a straight line as well. Okay, that particular point at this point here, going to be straight tangent as well. Okay, so what happen here, when you seeing something, when you once you manage to write down this kind of curve to illustrating or try to fit or using your right hand grip, then you immediately able to write down this. If you look at here, take note that the line is moving upward here. So it's going up upon the wire here, and then go into the wire, go back to the back of the wire. At this point means that the magnetic field at this flat surface we're going to be into the page. When it into the page, into means that it leaving you. So the analogy of an arrow is leaving you. You're going to see the cross, cross sign. So that will be the sign. So same goes here. The magnetic field at that this point will be cross, and this one for I1. So this is the direction of B1. Okay, do the same thing. Okay, do the same thing for I2. Okay, for I2. So same goes here. Have the right thumbs here. Have the thumb, and then you will have your thumb. You're going to have your thumb here, and then again the same figure here. The same figure. You will have the thumb here. Goes like that. Okay. So to understand here, it's much more easier if we use something that you familiar. Okay, so there's another rule of this, because you are that can be useful, because it's easier to determine one side and then the other just follow through. What I mean by that is, if you should I have understand just now, if you should have understand just now, once, okay, your right hand grip just now you use for this particular wire. Okay, so you're able to determine this point will be cross, will mean into the page and into the page. So at the other side would be dot immediately. Okay, so because you determine here this is going to be x and this one is going to be dot. Okay, so I give you example. Let's say somehow you ever determine this is dot, due to this current. Okay, due to this current. Due to this current, you have able to determine this one is dot. Then the other side immediately going to be x, or into the page. This is out the page. This one into the page. Okay. So the strategy is that you just need to determine one side. So the other side is going to be opposite of that. Okay. That is from one source. Okay. Okay. So same goes with here. So we can use what you understand just now. The thumb here, and then it's curved like that, and then you will get the curl to be like this in this direction. Then it will give you this one is x, for I2, for the magnetic field due to the I2, but we don't want this side. We want the inside, the inside side. So what happened, because this one is already x, the inside will be dot. Okay, so the inside will be dot. So the blue one is referring to the B2. The yellow x will be equal to referring to B1. Okay. Okay. So right now we need to remember, eh, the out of the page. The direction usually going to be like this. Eh? X is positive, Y is positive. Okay, and then Z is positive in this direction. All of this direction I've shown you is a positive values. So that Z here, what you're seeing is actually is out of the page. Okay, so out of the page is are going to be a positive values. Okay, so here B2 going to be positive, the dot going to be positive, the X going to be negative values. So when you do the summation and the resultant summation, so whatever value for B1, you input the value, but V1 is negative, so you add a negative value. When you do this calculation, it's okay for you not to get any positive or negative value. Uh, eh? But when you add the summation, do remember, or you can immediately add this one B1 to be negative value because it's into the page. You can do that, and there's no problem. But the most important part is that when you do the resultant or do the summation of the total magnetic field at that particular point midway between the two wire, you need to include the direction respectively to the direction whether it's into the page or out of the page, whereby the out of the page referring to the dot will become positive, and then into the page referring to the X mark will be the negative value. Okay, so that's what all this thing shows you. Okay, but this one is very clean and everything. You don't quite understand why it is. So the most of you practice. So I'm going to say it again. What you're going to do, which is a bad thing, you're not going to benefit it. eh, at the short time. If you do enough, maybe you can get it right, and maybe you can benefit eventually. But if you want to benefit it immediately, you need to apply your understanding. Don't adopt the solution given as you given here. Don't adopt this solution. What I mean by adopt, you see what they did, you just follow what they did at the other tutorial or other exercise. That if you even got the answer, that is not something you should proud of, because that kind of thing will not, you will not benefit from it. Because if I were to give you the same question what you did just now without without giving you the solution, the example solution like this, you won't be able to do it immediately. I can assure you. Saya boleh janji kalau awak buat ni, awak buat satu soalan, awak nak refer dia ni dan awak isi dapat value soalan tu. Lepas tu saya bagi lagi sekali soalan yang sama, saya tukar nilai sikit, you immediately cannot do it. Believe me, even if I given you the equation, awak takkan dapat buat, percayalah. Okay. So this is what you should benefit from here is what the thing that you should have in your solution. Jawapan kena ada unit, give the direction into the page or out of the page. So this is the safe way. Although that I mentioned to you, out of the page is positive, into the page, out of the page is positive, into the page is negative. But this is the safe way to we don't have the apa nama tu different opinion on that. But if you look at here, it's also mentioned that so this kind of thing is very confusing. So I'm going to show you what does it mean. Okay, 1.6 times into the page. So this is the vector here. This is a vector. Out of the page, also a direction. So this is a magnitude. This is the direction. This is magnitude. This is direction. Okay. So you can't add these two together based on what they show here. I don't recommend you do this. I don't recommend you do this. You can just simply put a negative or positive value by showing like this. You can immediately put a negative value and then describe why it's negative because it's out of the page. Done. Okay, and then you don't even need to do something like this because it's if you can understand what about it, try to explain, you can use it. But if you somehow think this is somewhat much more confusing, so don't use this. Just simply add negative or positive according to the direction. If it out, leave it as positive. If it into, then add negative in front. Okay, coming back to here. So this is what happened. Okay, once you know the direction and then you know the magnitude, so you get the magnitude and the direction, then you add another magnitude field with the magnitude and direction. Remember, because this is a vector, so you need to do the same thing. Okay, so what happened to the next line here? The first one is still into the page. The second one is just now is out of the page here. Is out of the page. You need to make it the same so that we have the same technically like we can factorize it out lah. So to make it more sense, once we make it the same, we can factorize out. Know this, we can also do it the other way around. Okay, I will show you later. Okay, coming back to here. So dengan kata lain, macam untuk factorize kan. So instead of out of page into the page, we cannot factor it out. So we need to change out of the page into become into the page. So apa maksud dia? Macam saya pernah cakap dulu. No, I didn't teach you that one. So in a way, okay like that. It's upward. Okay, this one we call it upward. Okay, this one we call it upward. But I can also mention this upward negative backward. Negative backward. So this is a positive upward. This is a negative backward. So these two are equal. A negative backward, downward. Negative, positive upward equal to a negative downward. What I mean by that, a negative to down is a positive, which is up lah. Or I can also put it a negative upward is equal to downward. So that what it mean. So apa yang berlaku ni dalam ni? So it mean that you have like 2 upward plus 3 downward. So how can I change this one so that I can factorize the upward? So I need to change because I want it to be upward. I need to change the downward into upward. So I put it this one upward plus 3. So downward is equivalent to negative upwards. Okay. So then it becomes 2 upwards minus 3 upwards. So when you add it together, you're going to get a negative 1 upwards, which is technically 1 downward. Okay, so something like that. Okay? Or you can also solve the same thing here. Instead of changing it to upward, you can change it into to negative downward plus 3 downward. Okay, plus these two, you will get negative 2 downward plus 3 downward. That will give you 1 downward. Same answer. Okay, same logic, same application for this. So I don't need to explain the other way around. Okay, so if you change this one into, instead of into the page, the outer page into the page, I can also change, instead of that, I can change this one into, not this one, just leave it at that. So this one out of the page. So I will remove this one. So this one also remain out of the page. I remain out of the page. So just now is positive. So this one should be positive. This one no. Yeah, this one just so this is out of the page. Just now it's into the page. I make it out of the page. Then become negative. So you add this thing together. One is negative. One is 4. So you will get is a negative 0.4 times 10 power negative 4 t out of the page. So did you get the different answer? No, it's the same answer, because into the page, a positive into the page is into the page, but negative out of the page is technically opposite of that, which is into the page. Negative out of page is opposite of the out of page, which is into the page. Technically, you get the same answer. Okay, so that's how the solutions work. So same goes with down here. Okay, okay, okay. Let's us go to the. Okay, so for the second part is the same question. The same question. It's only that in this case the current I2 here is the opposite direction or I1. So what does it mean? I1 remain the same, but I2 is moving at the negative direction. So what you need to do the same thing. B1 you already calculate. B2 technically is the same. It's the same because it's still midway. Okay. So what are the difference is that the direction of B2, because just now is the current is to the right. The second question is to the left. So again, check your uh, right hand grip. Check your right hand grip and then check the direction. So find the one either of side that you are comfortable. And once you determine one side is dot or X, then the other side should be this opposite of that direction. Okay. So okay, good luck trying that kind of question. Yeah, this question. You can try out this question. So I will not wait. Yeah, so you can try out later. Yeah. If you do have any problem, again, try to check back the video. I'm going to leave this video. I'm going to upload the video in the YouTube, so you can go through again at this particular time. So hopefully the recorded video will work just fine. Okay. And then of course, if you do have any problem and we don't have that time to discuss here, it's also inconvenient. But if you do somehow in midway, you can try, as I explained, you can try it. And if you do have any question, I gladly to explain to you if you don't understand uh, how to solve this. But in exchange, I also need to know which part that you stop. Okay. So not simply, I'm not going to give you the same solution as this. So this is the same solution. As I mentioned, don't adopt it right away, but understand it and then write down yourself without referring to that previous example. Okay, don't refer it to the previous example. You're going to waste of this question. This question, you're going to waste this example. Okay, awak akan rugi. Example ni awak akan rugi. Sebabnya apa? Because you just simply, uh, you know, macam buat awak potong tampal sini, potong tampal sini balik. So you're not going to learn. So the thing that you need to understand here, and then you think that you already understand the solution. Why did he did do this? Why did he do that? Okay, what are the steps been discussed here? And then use that understanding what you thought you already understand in this example. Do that. Take your time. So here we don't have that time. So do it, and then hopefully you haven't passed your tutorial session, or you can again you can always PM me, and I'm gladly to explain to you. I can also create a short video to explain this one, and of course the outcome of short video I'm going to share with the others. But again, I need to know what you don't know. I cannot simply provide you the solution step. It's going to be waste of example. Okay, so try out. Try out. You can pause the video and then try out. Uh, Maybe I will provide the solution later. Okay, but I don't want to provide right now. Okay. Um, let's see. Okay, the next one. I'm going to thoroughly explain the example. If the part of the question does not include example, then we can do that. So this is also the same. Okay, the next one is the current, a coil current, coil current, where you're going to utilize this equation. Okay. The magnetic field here is at the center, at the center of the coil. That is the magnetic field given there. And how to use it? This one is very direct. You just need to identify. So in this case, a circular coil of radius 40 millimeter consists of 250 turns of wire in which the current is 20 milliamp. Okay, a circular coil of radius 40 millimeter consists. So this is a radius of current R. Consists of 250 turns. So this is N. In which the current is 20 milliamp. So this is I. So remember, and remember many times. Uh, that you need to aware of the unit. Change every unit into SI unit before you do anything. Before you do anything. Okay. So you can simply write down what is R is that thing is 0.04 meter. Done. I what is current is 20 times 10 power of negative 3 ampere. Done. Okay, like that. You do there won't be any mark given to you. If you immediately write down like this, done. It won't be deducted. You will get the full marks. Okay, as long as you got it. But at the moment you just simply write down like this, I cannot save you anymore. You got it wrong already. Okay. So this one is just immediately put every all the values. But you need to see the question is at the center. So it's only valid for the center. So this one you don't worry. There's no kind of question that you're going to be asked either place. Even they don't specify at center, it should be at center. Should be at center. Okay, so that's a coil, material for coil of wire. So if we run more coil of wire and then it has a certain kind of length, it's going to become a solenoid. So this one, again, you can just simply apply the the equation. So this is what you're seeing here. This is another way of representation of a solenoid. Okay. So but this one it has an yeah, yeah, okay. So this is another representation. So this is the current goes in and then the current goes out. So something like that. Okay. And then goes the other way around and then dia turun kat bawah sini. Lepas tu patah balik sini, naik atas, pusing balik itu. Masuk bawah sana. Macam ni. Dia tak apa-apa sangat. So masuk bawah sini, betul naik atas. So yang atas tu saya highlightkan lah. Okay. So that will be the current. Macam tu. Okay. So same goes with the picture here lah. So kalau awak tengok sini, dia sebenarnya dia akan sambung jugalah bawah tu. Akan sambung itu. Dia akan sambung. But we don't see the bottom side. We only concerned about the top side because it gives us enough information. That's all. Okay. What we can do here, we can practice a little bit in terms of direction. I think the calculation maybe we can have a little bit question and answer, a little bit of interaction. we'll see if I can't hardly get any response, so maybe I will just move forward. We don't want to waste any more time. Okay, so let's say if I were to have a coil of wire here, so this is coil. So the current here moving counterclockwise, what will be the direction magnetic field at the center of this coil? Is it into the page or out of the page? I give you 10 seconds to answer before I answer the question. Okay, the answer is out of the page. It's out of the page. The symbol will be just a simple dot. Okay, so since that this is dot, so the outside will be X. So if I were to have a current I in this direction, what will be the magnetic field direction at this point? At this point, at this point, what will be the magnetic field? Is it into the page or out of the page? I give you 5 seconds. You can guess or you can shout the answer. It's going to be out of the page. So once you know this is out of the page, immediately this one is going to be into the page. Okay. So find a site where you can identify easily using your right hand grip to determine. You need to practice until you get it right. You need to practice until you know how to fit your right hand grip in order to pointing to the right direction, as I described here. So once you got one side, then the other side is going to be immediately opposite of that. Okay. So if I were to have another one current here, so here also if you look at the pattern, left will be, because it's the same direction, left will be dot, right will be X. So for the yellow one, this one will be dot, then this one will be X. But at the right side of the yellow will still be X for the blue wire. Eh? As for the left side of the blue wire, for the magnetic field due to the current yellow, will also still be dot, because here is dot, and then here is still at the left of the yellow wire, so it's still going to be dot as well. Okay, so you are seeing here the magnetic field here at the center will be less than the magnetic field at the not necessary. That one you need to calculate. Not necessary because of the distance also part of the factor. Okay, but if you close up together, that might be different. Yes. Do you have any question? Okay, let me continue. Okay, so this is example. Again, for this problem, also going to be more direct. The one that is going to be usually a little bit tricky is the first part just now, the single wire, because we can have a lots of configuration. Can have lots of configuration. So in this case, uh, I'm going to just follow through with this example. So a thin 10 centimeter long solenoid used so a thin a thin 10 centimeter long of solenoid. So this is going to be the L. Okay, for the fast electromechanical switch has a total turn of 400 turn of wire. So this is going to be N. And carries a current of 2. So this immediately going to be I. Calculate the. So the equation that is here is this one. So once you know the respective equation, then you identify the given what is the variable for each value given there, then it's going to be very obvious how to determine. So here remember there's the two equation. So B equal to mu, and I think this one is going to be provided in your list of equation, but I'm not quite sure this one. But you always can remember that N is equal to N base over L, where the N is the number of turn per unit length. Numbers of turn per unit length. So this is number of turn. This is unit length. This is length, not unit length. This is length. So that's what given by the number of turn per unit length. Okay, so maybe we can try out this one of the example here. Show you immediately before we go to the two parallel wire here. So just now actually we already have a two parallel wire. Oh, but this one is false, eh? Okay, because that one is much more tricky. That one I think going to be focus. Maybe this one I'm going to skip. Okay, because this one I'm going to give you a few example. I'm going to run through, because this one is related to similar to the first one. Maybe we can go to this one lah. Okay, holiday usually is much more difficult question, so we go to the survey first. So holiday you can try it out yourself. Okay, so what is the current in the winding of long wire? So this immediately become B equal to mu naught N I over L. Okay, so what is the current is required to in the winding of a long solenoid? Okay, that has 1,000 turn. So we have N here, uniformly distributed over a length of 4. So this is L. In order to produce a magnetic field of magnitude, so it's already given us B at the center of the sun. So the question asked is the current. So you can see here immediately. So current is the one that we're looking for, and it's been given. Mu can be obtained. B is given as well. L also given. So the next thing is just a mathematics. Very easy and very easy. I think shouldn't any one of you should not be able to answer this unless you have some on the question you don't understand what does it mean. So indeed, in that case, if you somehow find yourself in that situation in such a way you can't understand really what the question is about, you can always ask. And don't ask what the question want. Don't ask that way. You should ask. Let's say you don't know is what winding is. So you ask the people, can you explain what is winding? I don't quite understand uh, this term. So technically, this winding is like this. Winding. Winding means that you have a road. You wind a wire. You don't need to have a winding with a road, but usually that's the terminology. You wind something on a wire, on a road or something. So you wind on something, but you can also have a simple wind of wire without having to wind it on anything. Okay, so technically that's it. So you arrange the equation. Make the I because you're looking for the I. So beta B, magnetic field here. Magnetic field will be equal to multiplied by L mu n. That's all. That will be the solution. Put the values, you immediately going to get the value there. Okay. Okay, so the next one is the force. As you remember in our previous discussion, before we take our leave, before last week, it's technically it's 3 weeks before, quite a long time. So I'm going to going to be considerate and then go a little bit on what we are left, following to the notes. So I can just explain, write down the explanation, but I'm going to explain through the notes, so that you can always refer or benefit to the things. So this is what I mean. Okay. So this is what I mean. The force, the magnetic field force due to the current. If you remember before that, we have the due to a charge, QVB, but that one is for current. So we're going to use this. Remember, this is the magnetic force experienced by this wire. I is the current in the wire. L is the length of the wire, but B is not the magnetic field of the wire. It's not the magnetic field produced by the wire. What I mean by that, okay? So if I were to write down here, B equal to mu naught I over 2 pi R. Okay, so this magnetic field, if I were to put one I, this I1, B1, and then this is I1 here. So this is what I mean. And if I were, this is I1, and then I put it I1 in here, okay? So in this case, this magnetic field is magnetic field due to the current. But here, this is not B1. This is the B outside, external. External can be come from the others many kind of source, but it's out external source. It's not from itself. Okay, so remember that. Okay, remember that. We're going to make use of that. Okay. Uh, so we're going to also discuss again the question is always going to be like this. This is a vector form. It's a cross product, but it's going to reduce to this. Most of the time, you're going to have the theta going to be 90 degrees, but I'm going to emphasize on that in each part of the example. Okay, coming back to this one. Okay, make you inshallah I try to upload the without depends on how long the video is. So hopefully this working fine the recording. Okay, where is it? Where? Okay, I think I skipped. Right. Oh yeah, this is Magnetism. Okay, okay, this done. Okay, I think I forgot where did I stop. Okay, here is it. Okay. Okay, so what happened here? Okay, try to not to look all the pictures there. There's another way to look at it. This is I will explain this one. Okay, this is not part of the topic here actually. Okay, um, so how can this force coming to this point at this how it will end up with this force? There's a chronology. There's a step how this happened. Okay, so we have current I1 at the left here, and we have current I2 at the right. Okay, so remember, use your right hand grip, right hand grip for I1 here. The left side of the I1 will have the magnetic field in what direction? Give you 5 seconds to think. You can shout the answer if you know right away. Okay, the magnetic field will be upward, outward, out from the page, out from the page. Use your right hand grip. I already mentioned just now. If you don't remember, you can always check back again. Okay, so once you got this one direction, so left side, the right side will be opposite of that. So this one will be opposite. This one also the same. And this one all from I1. Here, 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 on top of the current I2 everywhere as long as on the right side of the current I1 you're going to be into the page because on the left side of the current already out of the page, so the right side of the current will be into the page. Okay, what about I2? So if you look at it, it's the same direction, so technically it's the same lah. I2 because I1 just now left will be out of the page, so I2 at its left also going to be out of the page. This one out of the page, out of the page, out of the page. This one is still at the left, also going to be out of the page. This one is already out of the page. And the magnetic field is everywhere. The magnetic field is everywhere, all of the places. So because of the left for I2 is dot, is out of the page. So the right will be into the page. Okay. So this one will be into the page, into the page, into the page, into the page. Okay. The yellow one is referring to the I2. The red one referring to the I1 magnetic field produced by magnetic field. The red one is magnetic field produced by I1. The yellow one is magnetic field produced by I2. So what are the equation? The equation is B1 equal to mu not I1 2 pi r. So the r here is the distance from I1. We can label this R1 because it's a perpendicular distance. It's the shortest distance from the center here. It means that kalau if I were to have a point here, so what will be R1? It's not this. It's not this, but exactly 90 degrees. That will be the distance from I1. So this will be the R1 if the position I'm looking at here. Okay. Okay. Of course, for the um for the, let's say, R2, for the R2, I2, sorry, I2 also going to be the same. But here B2 is due to the current 2. 2 pi R2. So what is R2? Let's say we're looking at the same point here. So that will be the distance. Okay. So then this one will be the R2. Okay. Not just simply the same value, put everything, just put everything that you find R, just fill in everything without thinking. So that's a bad way. Okay. So you should take a moment to think what is being given, what you understand, what the equation mean. Okay. So that's what happened. So what you're seeing here, what you're seeing here, if you look closely, what will happen here, we'll have, we have at I2 here, we have the magnetic field only from the produced by the, okay, I got this one confusing. So I just erase this because it's, let me just write down here. This is I2. Okay, so I2 is with the blue, the yellow is I2. eh, the yellow, the yellow is I2, the red is I1. Okay, so if you look at here, the magnetic field at I2 here, remember before this we have the F equal to ILB sine theta. Okay, so this force is experienced by by one or at the current one. This is current one. This is the length for one, and then B is not one. B is external. So if I were to look at the I2 there, so means that what is the force experienced by I2 is F2 lah. So going to be I2, depend on the I2, depend on the length of the current, and then depends on the magnetic field at, not not I2 magnetic field, but magnetic field at at I2. Magnetic field at I2. So magnetic field at I2 is this one. Okay, is or at the on top of the current, at exactly at the current, at the wire, exactly at the wire. So you can't have magnetic field produced by I2 at that current itself. You can't have that. And you won't be able to have that. And same goes with I1 here. You can't have magnetic field produced by I1 at the current I1 itself. Okay, so what you're seeing here, the same thing happened for I1. The magnetic field at exactly at the wire is due to the magnetic field externally produced by I2, from the current I2. So what you happen here, you just simply need to determine this B, this B. So the sine theta here, if you look at here, the direction here is upwards, and then the magnetic field is into the page. So if you somehow find your paper there, you put it on the table, and then you try to point your pencil or pen directly into the page, you will see that that paper and your pen will have a 90 degrees. So that will be sine theta here, the theta here going to be 90. So that will reduce the equation into I squared, I know I squared I to L2 B. So B here is the external magnetic field at current 2, which in this case is due to the I1. So what is B? So B is B1. This one B here is actually the B produced by current 1. So B1 equal to mu not I1 2 pi R. So because we are looking here, this R is the magnetic field at the position where is I2. where is I2? So then the R will be this direction, this distance. That will be the R from I1, from the source, okay, to where it is that you are to try to determine the magnetic field, which is at the current I2 here. So that's how it is. So I hope I clear the things up. Okay. Okay. So how can we determine the direction? So that's how it's just how you to formulate the value. But then how can we determine the direction? Okay. So this one you can again you can use the Fleming left hand rule. Fleming left hand rule. Again, the point in the index finger, index finger tu jari telunjuk Jari telunjuk sentiasa you use jari telunjuk tu untuk point the direction of magnetic field. So let's say we try to do the I2 first, the force apply the force the magnetic force act onto the I2. You use your index finger, everyone do it. Use your index finger, point towards the direction of magnetic field. In this case, is the red X too. The red X is pointed towards the page, into the page. So you point your index fingers into the page at your screen there, or at your if you have your notes there, into the page. And then the next one, bring out your middle finger and then rotate your hand while maintaining the index finger pointing to the direction of magnetic field, and then rotate your hand until your middle finger point towards the direction of current I2, which is upward there. And then once you do that, you bring out your thumb. You're ready to point the direction of force. Then you will find yourself pointing to the same direction as been given in the notes there. Okay. Okay. So you can also practice the same way here. Okay. I will do this one immediately. So this is I1. Okay, the magnetic field. Use your right hand grip. Okay, right hand grip. So the left side of the I1 will be the magnetic field will be outward. Okay, once you got this side, then the other side will be opposite of that, which is cross, which is into the page. Of course, until everywhere, as long it is on its right. So here also going to be into the page. Okay, so maybe with this time we try to do the yellow one. So here the I2, we try to determine the check for I1, force at I1, F1, F1. Okay, what we do again for I2, what is the magnetic field produced at the left side of the current? So use your right hand grip. You will find out that this one also going to be into the page. So once you got this side is into the page, the other side going to be out of the page. And then this one also maintaining into the page as it is still at the left side of the I2. So here you will have into the page as well. Okay. Okay. Then if you want, because of this, we already know the direction of magnetic field as well as the direction of current. So if you want to confirm the direction of force, we can use what you did just now. Okay. We can do what we did just now. So we bring our index finger while closing all other finger. Just bring out your index finger. You don't need to pull out all other finger just yet. Use your index. Bring out your index finger only. Point towards the direction of the magnetic field. At the point at the position of the on top of the current I1 just now. We try to determine the direction of F1. So point to the direction of magnetic field. In this case, is still X. Or cross means that it's into the page. So point into the page, and then once you're ready, we have pointed into the page. You bring out your middle finger, and bring out in such a way that it is perpendicular to your index finger. That is comfortable. Don't break your finger. Okay. Then once you've done that, you can rotate your hand, your palm, while maintaining pointing towards the direction of the magnetic field. So rotate until your middle finger point out to the direction of I1, And then once you're ready, having both uh, index finger pointed towards the direction of the magnetic field, which is into the page, and then your middle finger pointed to the direction of the current, which is upwards. And then once you have both of the finger ready, you can bring your thumbs out, and then you will point to the left as in the figure. And you can also practice for F2 as well. Okay, you have your notes, so you can try yourself. Okay, so what you see, what I'm going to show you right now, it is when what happened when we have this magnetic field overlap each other like this. Okay, as you know, the magnetic field line cannot cross each other. So what happened here? So, for the left side, it's going to be in that direction. For the current from the left side, for the right side will be in this direction. So if you see this, because both of them have the same magnitude, okay, the same magnitude, of course, and this one is going to be the midway, and mean that both of them are going to have the same magnitude but opposite direction. So what happened here? The middle one is going to be cancelled out. So what happened here? You will see that it's going to be something like this. The magnetic field. It is going to be somewhat connected. Because sorry, this one wrong. Okay, somewhat connected. Okay, and you don't have the middle one here. You won't have any magnetic field. Okay, because it is already overlap each other. And it will cancel each other. It's going to be like this. So if you look at here, so you can imagine because there's no magnetic field anymore here, but you have magnetic field outside here. So you can imagine that this magnetic field line like a rubber band. Okay, so when you have a rubber band outside, then because it's stretched out, it's been stretched, so of course you're going to be pulled inward. So that's what you call being attracted. Or you can also use this concept as well. You can always play around with this. You can draw and then play around with the magnetic field, and then use your left hand Fleming left hand rules to point out the direction of F. At the moment you see that both of them are point out each other, of course, it's going to be attracted. Okay. Another way you can use the analogy I've showed you just now here, this one, because there's not going to have magnetic field in the middle, whereas they're going to have magnetic field at its side, both side. So if, as I mentioned just now, it's going to be like a rubber band because it's stretched towards the left and right here. You're going to have more tendency towards each other. So that's what I call attractive force. So whereas the other way around here, remember, as uh, as the magnetic field can't cross each other. So once you try to bring these two together, you will see that this magnetic field direction is this way, and then this one is magnetic field also in this way. So you're going to have a very dense or pack of line. Eh? Bayangkan kalau saya rapatkan ni lagi. So line ni, this line and then this line cannot cross each other. So it cannot overlap each other. So what happened that it's going to compress, means that it's still going to be side by side, but eventually it's going to be very packed in line. Dia akan rapat. Kalau tak ada kawan sebelah, kalau tak ada kawan sebelah, it's going to be far. But because of the kawan sebelah ada, let me fix this one. Because of the kawan sebelah ada, it's going to be like this. Sebelah kanan ni, because there's no other magnetic field line, but in the middle here, because we need to share the close pack area. So then you will see that there's a very pack of line. So compared to this, to the outside of this, you have less pack of line. So it will have more tendency to push away from each other. Okay, so that's how you can make use of to what you call that, to provide you a common sense out of this phenomena, or you can also observe what happening here. It is technically opposite of the situation of what usually happen. Positive attract negative, but in this case, the same direction will attract each other. Opposite direction will repel each other. Okay, so that's one way to identify lah. Okay, you don't need to remember this equation. You don't need to remember the equation. Do one thing at a time. One at a time. This is what I explained just now. Okay. The F2 and the I2. This F2 it means the force act or felt yang dirasai. Force yang dirasai oleh current I2. So dia bergantung kepada current I2. Dia bergantung kepada length. Okay. Tapi dia bergantung kepada external magnetic field. In this case is I1. Kalau saya buang I1, tak ada dah force. Sebab tak ada magnetic field. Okay. So because of the I1 ada, kita kena ada. So in this case tak payah buat equation macam ni. You do one by one. Maksudnya awak selesaikan yang ni, dapat B, masukkan dalam equation. Masukkan equation B yang ni. Masukkan je B tu, nilai B tu masuk dalam ni je. I, L. Sebab kan awak tahu all of this is sin 90 degrees. So then it will just BIL lah. Okay, this is 2, this is 1, this is 2. So going to be like that. Okay. Okay, so this is something you should know. Once you, again, you don't need to remember this. You don't need to remember this. Again, you don't need to remember this. What you need to know how to use is this one and also F go to BIL. You will end up with this. You will end up with that. Okay, only that you need to know force per unit length. What does it mean? It mean that this is force and this is length. So what will be this one equals to for this case? For this particular chapter case, it's going to be BI. Okay, BI. So what is B? So this is, let's say this is 1, this is 1, this is also 1. So this B is the external. So if you have a current I2 that produce this magnetic field, so then this one is going to be B2. Why is B2? This one. Do one at a time. So this one you don't need to remember. You don't need to remember. You just do one at a time. Okay. So ni pun sama, tak payah remember. Okay. So something you can make use of, cut short. Cut short with the solution. By having this, you will see that there's not much of difference. The force is going to be equal. F1 and F2 akan sama. Dia punya force because like um, positive negative lah. Okay. Although that this one might have two negative, but the repulsion force is still going to be the same. The force applied felt by the negative will equivalent to the force felt by the positive. So same goes with here. Because there's two things. Because the logic is one thing, and then the equation will going to be similar. Even if you change into force too. Kalau saya tengok sini, saya tunjuk. So this is what we have is F1. If I were to determine F2, so end up with this. It end up with this one. If I were to make F2, so this one will become B1, I2, L. So if I were to put the value B1 tu, so ni I1 to pi D. Okay. So this is the D is the distance between the two wire. And then we have this I2 L. So if I were, if you look at here, if I were to put everything together, this one going to be mu naught I2 I1 L over 2 pi D. As for this one, if I were to put everything together, mu naught I1 I2 L over 2 pi D as well. So if you look at this, these two are exactly the same. It's not similar, it's exactly the same. Yeah, what the difference is I2 multiplied by I1. This is I1 multiplied by I2 is the same. Eh, the value going to be the same. So that's why it come with this lah. Okay. So you need to understand what I mean by per unit length. And force per unit length is simply divide by the length itself. So awak akan dapat Newton per meter per meter. Newton per meter. Okay, example of this, two wire of 2 meter long. So this one too long. Okay, this one required lah, because it's just 1 point. The two wire 2 meter long, apply the cord 3 millimeter apart. Maksudnya dia sini draw, this is 2 meter. Two wire So you have dua wire sini, 2 meter juga panjang dia. And then apply 3.0 millimeter apart. Maksudnya jarak dia ni adalah 3.0 millimeter. Carrying a current of 8 ampere. One wire exit on the other. Kejap Calculate the force. Okay, this one it doesn't mention the direction. Wire long pan. Calculate the force on wire exit on the others. So presumably it is upwards lah, both upwards. And okay, if it both upward, if you remember just now, it's going to be repel. Okay, going to oh no, both upward is attract. Sorry, you're going to attract. Both upward is attract. So yeah, just simply put the value lah. So if you don't understand calculate the force wire exerted on the other, maksudnya you just need to find either F1 ataupun sorry, it's not that direction Okay, in this direction. So either you determine F1 or F2, both of them. So in this case, again, you don't need to use this equation. You start something that you already know, which is you are given to wire. Okay, which is find the force either way lah. Okay, F equal to I LB. I LB, and then you have the current, you have the length. The force you need to find the B. So B. So B is mu naught I over 2 pi r. Okay. Okay. So here, the r here is the distance between the two wire. Okay, the distance between the two wire. Okay. So once you got this, let's say you will determine this one F1, F1. So this one must be B2. So 2, 2. So this is r is the distance apart. Okay. So once you got this, put in this value, you immediately get F1. That will be the answer. Do it this way, you still get the answer. So as I mentioned before, I suggest you can use this if you really confident that you can remember this. You can use this. But this one, you definitely if you remember these two, okay, if you remember this two, definitely you can still use this. But if you just simply remember this, you might not remember this or this one. What I mean by having remember these two only, you're able to do that one. But if you can do it right away, there's no problem. Okay, you can do the solution exactly as this, but don't forget to write down the unit. Okay, so the other two is the same. Okay, all of them are the same. This one force between two parallel wire. Okay, yep, this is also going to be the same. Determine the magnetic direction of the magnetic field halfway. So this is, I think we already done before. Okay. Yep, this one we already done before. I already explained before. Force between the two parallel wire. Okay, wait. I don't quite understand the question. Which part? The two parallel wire? Okay, 5, 5. Where is the 5 and 7? Okay, I think the second solution, this one is wrong. Okay, force per unit length at a midpoint. Force per unit length at the midpoint. I don't quite understand. Maybe what does because the question does it ask you between the material direction of the material halfway between the two wire and the force per unit length. So no, I think this one. Okay, let me just double check what the solution so I can fix either one. Okay. Okay. So what does it mean? It's not the same condition. It's not the same condition. Um, the first question. The first question is to determine the magnetic direction of the magnetic and direction of the magnetic field. Magnetic. This is magnetic field. Magnetic field halfway between the two wires. So you are looking for the magnetic field at this point. But when they ask the force here, we don't have any current here. We don't have any current. So what does it mean? It means that one of the wire here is already at somewhere here. Okay. Means that you are displacing lah. Displacing the current. Current somewhere here. Maksudnya this one distance is become only 5 centimeter. Okay, so I think the solution is wrong. Force per unit length, because we need to have a current, but they don't provide the current. But if I were to tell you what is the solution meant, the solution meant that the one of the wire is moved towards the midway, so that the distance between here is 5 centimeter. So that's one. I mean, then the others is the same as I mentioned. I don't recommend use this equation. Use from the basic and then move around, play with the algebra lah. Okay. Let me just finish this one. Okay. Yeah. It's okay. I can just complete this one. For this one is again this correlated to the previous one, but then going to be a little bit of talk here, which is we don't cover any part of the chapter before. So what mean by talk is it is when you have a center. Center maksudnya in this case the talk here will be half of this and then half of that going up, and then you technically multiply by 2 lah. Distance between the two forces. Technically torque actually is equivalent to Fr. Okay, Fr is a distance. If I were to have a door here, okay, so if I were to push this way, so this is F and then this is R. The R is the distance from the pivot point. Pivot point is a rotation. This one you're going to learn eventually later. Okay, it's a pivot point here. So in this case, this is half of D, D over 2. So the distance between here is D. Okay, so this is F cos. It's a cos product. So here in this case, I will give you is the direction. What call that? It's a 90 degrees. Sine 90 degrees. So then we try to assume this one is also 90 degrees. Okay, so what happened here? This side only. This F is F sorry, torque. Torque is equivalent to Fd over 2. Okay, and then this one is also another torque, Fd over 2. But if you look at here, the torque direction here, I don't want to talk the I just the actual torque direction is going to be a different scope of direction. I don't want to discuss that. I just want to give you answer, give you the common sense. Okay, the torque here is actually try to provide in this direction, rotating to the counterclockwise for this F here. But for this F here also going to be counterclockwise. So technically, by adding these two torque, you technically add these two torque together lah. So that Fd over 2 plus Fd over 2 will give you just Fd. Okay, so that's what you get the only Fd for this one. And then this one is perpendicular distance between the force. Maksudnya distance between the force one and then another force here. Okay, so the thing that you need to know to identify the uh, force, there's a two thing, something force that you have learned before. So only this time you need to identify each segment, what the same what we have done before. Okay, so then we have in this case we have multiple segment. So this segment here. So how can you know what will be the force? Where is the direction of the force? You can again use the current. So this is I here. And if you look at I and B here, this is I, this is B, I and B. So the angle between here, you remember the ILB, F equal to I, LIB cross B. So I in this direction, B in that direction. This is B, this is I, and then this is 180. So if you break it down, I, B, sine 180, this will give you 0. Okay, so then there will be no force here. Of course, there will be no force here as well. Force equal to 0. But here, it is, current is downward here, and then magnetic field is here. So it's technically 90 degrees. Same goes with here. Current is this direction, magnetic field in this direction, also going to be 90 degrees. Okay, so where is the direction of the force? Again, use your Fleming left-hand rule. Point out your index finger, point to the direction of the magnetic field to the right, and then bring your middle finger, and then while maintaining the index finger pointing towards the magnetic field, rotate your hand until your middle finger towards the direction of current, which is downward there. And then once you're ready, both of the magnetic field pointed, and then also current is pointed by the middle finger, you bring out your thumb, and then you will see that your thumb is pointing at you. And if you're looking at the screen right now, you will see that your thumb is pointing at you, which is out of the page. Okay, out of the page. The force here is out of the page. And then if you do the same thing here, magnetic field at this side, at the other side here, will also going to be to the right. So maintain your current magnetic field index finger to the right as well. Bring out your middle finger, turn it until it point upwards, and then bring out your thumb, and you will see your thumb is pointing towards the screen, which is into the page, into the page. So what you're seeing here, so this one out, and then the other one in. Then you will see that it is somewhat rotate. This one will going to be rotating in this direction. Okay, in this direction. So kalau if I were to do this, so then okay, so that one will be at the back of the line. Okay. Okay, something like that. So again, remember there's going to be a pivot. But since that this is half, then you can just multiply by a. Same goes with that. Okay, same goes with the. Okay, in this case, what will be the torque? Ada tak example? I'm going to explain with the two examples here. So this is what I explained just now. This is what I explained. What will become a torque. And so same goes with here. what you're seeing here, F equal to F2, yeah, where is F2? This is F2, and then this is F4 is the same. So this is the same, IAB. So what is mean by AB here? Okay, A is the length, this length. A is the length, B is not this B, is the magnetic field. So technically this is F equal to I, L, B. So this is I, L, A here is the value of L, where L equal to A, and then B is the magnetic field. So because the magnetic field is the same, current is the same, the length is also the same. This is A, this is also A. So both of them force is the same. Okay. So if you look at here, F2 is B over 2. Why is B over 2? Because this is the pivot where it's going to be rotated. So this is the length of from the pivot point towards the force. So this is B over 2. And for F2, no, for F2 here, for F2. And then the same goes with F4, also B over 2. So you add up together, it's only left with F2B only. So you have the F2B, so the F2 and F4 is the same. So in add, you're going to have is F2B or F4B. Is the same, both are the same because F2 is equal to F4. And then what is F4 just now? We have I, A, magnetic field, but 2. Then we have B here. Then we have this I, A, B. So if you notice here, if you notice that A times B there, A times B, so this is A, and then this is B. A times B will give you the area. So this one also can be given as I area B. Okay. So with this conclusion, if I were to have a magnetic field like this, okay, and then I have the coil instead of square, circle, which is very difficult for us to determine which one the torque at every part of the circle. So we can just simplify taking the area here, the area of the coil with the magnetic field, and then this will be the torque. Okay, so that's the function of having been simplified like this. Okay. Okay. This one also I'm going to already explain. Okay. So this is. Wait, did I explain this one? Oh no. Okay, this one include with the angle, because I thought they don't matters about this. Okay, so here, if you remember, this is a cross product. So cross product, if you leave the cross product, you're going to be F magnitude times D magnitude times sine theta. So this theta is the angle between F and D. So in this case, so this is D. Okay, this is F. So this is the angle theta. Okay, you're going to be maximum when it is 90 degrees. Okay, so that's how you get this theta. So the theta here. So this is F, and then this is the what you call that? The B. Okay, the B. Sorry, the B. Okay. These two angle is going to be the same. It's going to be the same regardless. When you do sine. Maksudnya kalau you can try. Oh, it's already 11. Give me a little bit. Last I'm going to finish this one. Later, even you don't understand, you can try out and then try to understand through your exercise. Okay, I'm going to provide you this one last time here. Last thing here. Okay, so this is 60 degrees. So then this one will going to be 120. So 120 sine, and then all of 60 degrees sine is going to be the same. So If you look at here, the angle between F and B, it should be there, should be this one, but it's also going to be the same if you take that one as well. Okay. So if it's 0 and then also 180, going to be the same. Okay. So this is the equation that we established just now. This is torque. Sorry, yeah. The torque just now. Okay, I try to conclude this one. Torque equal to I A B. Okay, IAB, just IAB. And then sorry, this is force. Force equal to IAB. Because of this. And this is I, and then the length A, and then the magnetic field B. That is the force. And then the torque is equal to F cos R. Okay. No, in this case kita simplifikan terus because of the area just now. D lah. So in this case, the area just now, no, the area, the distance between the two force, which is this one is one force because these two doesn't have any force. Okay, the force F4 and force F2 here, the distance between these two forces is B. Okay, the distance between the two forces is B. And then we reduce, sorry, reduce this one going to be B lah. Okay, B. So what we have here is I, A, B. Because we want magnitude, then this is cos product. Then we have sine theta. So A and B, as we know just now, this is B. The distance between force, this is A. So A multiplied by B technically is given by the area. Area B sine theta. So technically this is a torque. So this n is actually, you can increase the number of torque if you have a multiple equal dimension of the coil. You technically make a wind lah. So the more you wind, the more current flow to multiple of coil, then the more torque you will have. Okay. So that's the thing lah. Okay. So the area here, um, what you're seeing here actually, this theta here, when it's reduced to this, what this statement given here, theta here is the direction of A and B. So if I were to have area like this, so the direction of the area is out of the page. If I were to have something like this, the area of this is out of the page. And then if I were to have magnetic field in this direction, which is along the page, then you will have this one as 90 degrees. So it is perpendicular. So this theta is 90 degrees. So if I were to have something like this, a little bit slanted, and then the magnetic field is in this direction, B. So this is the direction of area. So this will be the angle for this theta. The angle between the direction of B and then the direction of the face. The direction of the face of the area. Okay, the face of the area. Okay. So I think we're going to stop that one. If can, I'm going to just you can, if you have some other matters because you already make a deal, going to stop on 11. You can take your leave. I'm going to complete this recording for one example lah. Okay, so I'm going to explain this one example here. So a circular coil of wire has a diameter of 20 centimeter and contain 10 loops. So this diameter is D. Remember, the diameter is D. So this is diameter. It contain loops. So this is N. Current in each loop is 3 I. And the coil is placed to Tesla. So this is B. Placed to Tesla external material. Determine the maximum minimum torque exerted on the coil by the magnetic field. So minimum adalah, if you look at that, the equation is N IAB sine theta. So the minimum is when the theta is either 0 or 180. And that's going to be minimum. When sine 0, you will get 0. That will be the minimum. Very easy. Eh? For the maximum, it is when sine theta, when theta is 90 degrees. This is when you get equal to 1. So the maximum when this value is 1, and then the minimum when this value, this is maximum. Minimum is when sine theta equal to 0. That will be the minimum. Okay, so the minimum is right away. You can get the answer. For the maximum, okay, you need to find, because it's a coil loop. It's each loop, so it's not a square. So it's obviously going to be a circle. So you need to determine the area of the circle, because this is the area. Determine the area of the circle. Current has been given. Number of coils has been given. Magnetic field also been given. So determine the area. Immediately use the equation to provide the answer. So if you look at here, is 1. This is actually sine 90 degrees. Okay. And then the minimum, as I mentioned just now, is when sine theta is either 0, theta is 0, or 180. So both of these value will give the sine theta equal to 0, which means that you will give the whole equation reduced to 0, where stock is going to be equal to 0 lah. Okay, so that's all. Complete. We're going to end our discussion today with with tasbih kifayah suatu asa.